Let's get started. So my name is Anthony Lewis. I'm a program manager in NNSA's Office of Advanced Simulation and Computing, and I'll serve as the moderator for this session. First up, we have Nicholas Frontiere. He's from the University of Chicago. His field of study is physics. His advisor is David Reed, and he performed his practicum at Lawrence Livermore National Lab.
All right, how can everyone hear me? Just after break, so everybody's already upset to be back. But my first talk hopefully should be interesting. I tried to keep it high level to keep the time right, and so hopefully everybody can get a little piece of something from it. The title is pretty grandiose. It's trying to say that I work on the simulation team called HACC, Hardware Hybrid Cosmology Code. And the intent is we run simulations of the universe, and so we're trying to fit the universe inside a supercomputer, quite literally. And as you can see, this is what this picture is trying to dictate. This is the universe and all of its complexities. How do you put it in this generation machines, next generation machines? How do you handle portability? A lot of the stuff you heard about this morning. Now, I know when you see a title like that, you probably think one of two things. I'm either exaggerating or you just met a wizard. And sadly, it's never the second one. So I am obviously exaggerating. And it's not that we're fitting, it's not like we're simulating all the way to Earth. We're simulating large-scale structure of the universe. And we're going to go into that today. So let's just take a look at what that's involved. I like to start by looking at how cosmology fits in HPC first, because there's a lot of HPC people. The previous speaker had some way of characterizing HPC. This is my way, where I say, basically most of you fall in either one or more of these four categories. You're either trying to quantitatively predict something, get a number. You're trying to do some sort of scientific discovery or expose mechanisms, so you don't really know what your theory you want to use, so you start probing a lot of different theories, a lot of different mechanisms, and trying to discover something. You're either trying to do an impossible experiment, something you actually can't do in a lab, or you're trying to solve an inverse problem. You have a model, you don't know what the parameters are, the parameter values of that model should be, so you make a bunch of realizations and try to solve the inverse problem. This is generally, there's a couple other categories, but this is generally what goes into an HPC campaign. Why cosmology is interesting is it handles all four. We have a universal model that we try to make quantitative predictions with. It's an impossible experiment. You can't make a universe in a laboratory. We don't understand dark matter or dark energy, so we have a lot of scientific discovery that we are going through. And our model has parameter values that we don't know. And so we're solving one massive inverse problem at the same time. So naturally, we're an HPC campaign. And importantly, there's a huge role of scalability and performance. Not only do we want to run on massive machines with very large simulations, we also want to run a bunch of medium and small simulations. So not only do we require large machines, we also require high throughput, optimal design simulation campaigns, and analysis tools to boot. So cosmology really is a nice fit in the HPC world. How does it look in the physics world is kind of different, and you've heard a lot about this morning, which is great. We have this data overload problem. There's a lot of telescopes that are out today producing lots of data, and upcoming telescopes like LSST will produce more. And to give you an example, this is a picture of the sky that's just the size of the moon. So if you look up at the sky, look at the size of the moon, make a little square, this is how much detail you'd see if you used one of these telescopes and all of the galaxies they're in. The telescope LSST will be capturing 50,000 times this. Roughly 400 petabytes of data. So not only do we have to be big data analytic aficionados to analyze this, and machine learning experts to sort of mine it, we also need supercomputing expertise to predict it. And although I don't need you to take too much from these two curves on the right, their only purpose is to show, this is the cosmic microwave background for those who know what that is. Kudos to you. But the point here is just to say, look at these data points which are black, and look how tiny their error bars are. And this red curve is theory. And the only thing I'm trying to get across here is as these telescopes get bigger and bigger, the error bars get super small in our science. And so not only are we mining tons of data, we need theory that's accurate to the percent level or better. And so that's why we need these very massive simulations, and we need to really bang on predict our theory. So that's where computational cosmology and theory sort of fits in the physics world. You saw it as an HPC campaign. This is how it is in physics. All right, so now let's say I want to run one of these simulations. What am I talking about? Let's talk numbers. So a galaxy halo is roughly 100 kiloparsec. People, when they say how old's the universe, they say 13 billion years, so billion giga. So if I want to run a simulation, I'm going to need something at the gigaparsec size. And I'm going to need to resolve, let's say, a galaxy at 100 kiloparsecs. I might want a resolution of a few kpc. KPC to GPC, 10 to the 3, 10 to the 9, 9 minus 3 is 6. You need a dynamic range of 1,000,000 to 1, where your massive objects are 10,000 to 1. And while I talk about this, let me show a quick video of what one of these simulations looks like. So this is a 50 megaparsec box. The distance between Milky Way and Andromeda is like at the megaparsec level. And this is just showing the evolution of the cold dark matter of the universe, the primary massive component that goes into the lambda CDM model. And you can see all this substructure form over time, and you get what's known as the cosmic web. However, this isn't the size of the universe, this is a very small chunk of it. And what we actually need to run on a supercomputer is something like this on a much larger scale. And this image should show you sort of what kind of scale we're talking about. Almost. There. So that's about how big the universe is, and that's why we need big machines. And that's why we are super grateful to Oak Ridge and Argonne to let us use these machines. And this is really showing you that, in this simulation I'm showing is 1.1 trillion particles. They go bigger, and we use the machines as big as we can and as much memory as we can fit. So, and you can see that all scales matter. So to go back one slide real quick, I just want to end with, from a computer science HPC, what are the boundary conditions? We require at minimum petabytes of data to hold or petabytes of RAM, I should say, to hold the particle memory, and performance of at least a 10 petaflop class. So Titan and Mira and Theta fit well into this. And as you move on to things like Summit and Theta and exascale projects, these numbers get quite a bit bigger. These numbers do not, but the good news there just means with the same particle set you have, we can now do a lot more physics. And because of that, we're on a lot of the early projects for a lot of these machines. The last point to make is what physics is important. If I only care about large scales, so I only care about the density distribution of mass at large distances, gravity is the only theory that matters on those scales. And so if you run n-body gravity-only simulation, you can actually get this bang on correct, which is nice. If you care about something smaller, like galaxy formation, then you need to add what's called gastrophysics, baryon physics. Essentially, you need to solve fluid equations and then subgrid model things that are way beneath your resolution. We'll get into that a little bit later. So, quick formulas. I just wanted to quickly show that this is the Louisville equation. Many of you have probably seen in fluid dynamics. If this is the same equation you'd solve cosmologically, it's just Newtonian gravity. It's a 6D PDE. So if we were to do this on a grid naively, we'd have to have an n to the 6th grid times n for time. So an n to the 7th problem, and I doubt any of you would be convinced that we could run that at supercomputing scales. So the first thing you do is you got to integrate out the momentum of this equation. And if you do that, you end up with what's known as the Vlasov-Poisson equation. This is just jargon, but all I'm trying to get at is this is the original 6D PDE that we use, that we're technically solving. It's got extreme dynamic range and space and mass everywhere, so every scale matters. We can't just adaptively resolve certain places. And this is the equation we're solving. So how does one normally do this? Well, this has been done in plasma physics, it's been done in cosmology, and it's very simple. This is just an n-body problem. You discretize your fluid onto some sort of box. You move particles according to your field equation, and you're done. And this normally goes under the guise of what's known as particle mesh methods. You have particles, you initialize them somewhere, you solve the field equation, which in this simple toy model here would just be using one FFT. You can just see, oh, look, the Fourier transform of this simple equation is just this, phi equals g over k squared, done. So all I need to do is interpolate my particles onto a grid, solve the field equations, interpolate the force back to the particles, move them, and repeat. The problem is that the dynamic range is, like I said, 1,000,000. So to do this, you'd need a 10 to the 6th cubed grid, which unfortunately in that last slide I showed you, there's no memory. Right? You have tons of flops, not a lot of memory, respectively. So how do you solve this problem? Is what's known as the separation of scales solution. You run as big an FFT as you can, which luckily doesn't take a lot of the computational time, and all machines can do this. And then what you do is you've now separated sort of a long-range force contribution done by the FFT. And what that does, if you compute it on a coarse grid, is it messes up sort of the short-range force contribution. In other words, what that means is that if I look at a particle that I've solved with a coarse FFT instead of a 10 to the 6th FFT, its long-range contribution from all the mass around it was done correctly, but I need to make corrections to the contributions of the neighboring particles. It's that simple. Now, why is that good? What I've done is, once I finish the FFT, that I've separated my problem to now be a node-level problem, where all I have to do is run my FFT, and then now that I am at the node level, I can just look at each particle, look at its neighbors, directly interact with them, And that's now a very computationally intensive node level problem, not a distributed memory problem. Very nice for supercomputing, and if anybody has questions about that, we'll go over it. In fact, I drew a picture just in case to emphasize this point. So the way you do this is, here's the universe. You chop it up into the number of nodes you have. Each node runs their FFTs across, so that's your distributed memory task. And then once that's done, you go to each node and you make a grid, where the grid is at the scale of your short-range force interaction. And basically all you have to do is say, well, all the particles in this grid, I just need to interact with all of the neighboring particles. And I can either do that with a tree, which is n log n, or I can use a direct n squared method or other methods, depending on which machine I'm running on. So that's how gravity works. That's how you solve this Vlasov-Poisson equation. Now, like I said before, you might not only want to do that, you might want to add more physics. You might want to add gas, or even more enticing, you might want to add subgrid physics like active galactic nuclei, supernovae, feedback, star formation, ... means cooling, metallicity, morphology, all of these sorts of things. And so this is where really the dark arts of this field get to, because everybody has their own models. All I wanted to emphasize today is we've seen how big the n-body problem is for gravity. I'm going to quickly mention hydro, just because it had a very important role in my CSGF career here. Really quick to one method of solving the adiabatic equations, namely these, is to use what's known as SPH. I'm not going to go over it, but essentially for those that know, you are interpolating any field over some smoothing kernel. So if you have any field equation that you want to know what the field is at particle I, you discretize this integral, and you can basically turn each one of these fluid equations into a discretized fluid equation here. And this method has known to have a lot of problems with it. And when I actually did my practicum at Livermore with a completely different group, focusing on plasma physics and other things, we pioneered a new method called CRK-SPH, where, since I have no time, I can't really go into the details, but the punchline is these kernels are higher order. The formulations are, this thing preserves momentum and energy conservation. It's got new artificial viscosity for those who know what that is. And it was, like I said, developed during our practicum. And this is actually, I can't underwhelm this. This is used now in collisionless plasma physics, asteroid collision tests, all of this stuff. All of that was pioneered by myself, Cody Raskin, and Mike Owen during my practicum, and it continues to be an integral part of my research. And I thank the CSGF for giving me the opportunity to do this. Here's a quick example. Once again, you're not going to learn much if I can't talk about it much. But all this slide is supposed to convey is this is sort of showing some of the problems with the old methods. You had this issue where things did not like to mix for various reasons, and this is a Kelvin-Hamilton-Rayleigh-Taylor problem. And this is sort of the new method. You can see how you get a lot more mixing in these sort of fluid shear problems, and you get a lot more resolved edges. And I put PSBH, which are these two guys, for reference. This is just another modern form of hydrodynamics that people also use, and it just shows that ours is indeed achieving a higher level accuracy than the normal old SPH is used to. And this is just showing a quick simulation where this is the old way where you can see everything sort of smooth, whereas the new way is a lot more detailed. What does this look like when you do gravity? Well, it looks like this. If you run a gravitational simulation, everything clusters. This was the video I showed you before. If you turn on hydrodynamics, it basically puffs out everything. Just like a star, when mass collapses, you have pressure forces that react back, right? It pushes, an outward push because fluids don't like to be compressed. And similarly, if you run a universe simulation with just adiabatic hydro, nothing else, it sort of puffs out everything. And the only thing I want to emphasize is these solutions are clearly different. So you can already see why, from a large scale, gravity handled all the effects. All the dots are in the same place. But if I cared about the smaller scales, I need this effect. And then if you will care about even smaller scales, you need to do the subgrid physics that I talked about before. So we've gone over how you solve gravity. We've very quickly gone over how you solve hydro. And if you have questions at the end, I have tons of backup slides. The final thing I want to talk about, and it was really funny that Barb and other people this morning talked about Roadrunner, because I put an image of Roadrunner because it's still relevant today. And that's quite surprising when I first went to Los Alamos and worked on this machine. But essentially the challenge at the time, which turned out to be the challenge of the future, is you have these sort of nodes that have a very slow inner bandwidth communication, so you're not going to get much speed in between them. You might have tons of levels of memory hierarchies on each node, slow memory to maybe fast memory to even faster memory. And then you might have chips, which are like either accelerators or something that gives you your flops. And the point here is that I call these architectural features. I don't like to use the word problem because problems make it sound like they don't have solutions. Features are just additions we have to worry about, which is a nice way of saying that they're problems. And the idea here is that you have complex heterogeneous nodes, as was talked about this morning. You have very low memory per core. That's an issue. You have skewed compute communication balances. What programming models do you use? What I/O systems do you use? Etc. What I wanted to talk about was, as I said before, computational cosmology seriously cares about running these problems on multiple platforms. And so I just wanted to tell you that the way we solve this problem is we write our FFT codes in C++ plus X, where C++ is the MPI codes, and all of our computationally intensive kernels are written in whatever domain-specific language that machine requires. And that's how we're able to combat this diversity and run a bunch of machines. I know I'm out of time, so I just want to show you the results of that. If you run on the BGQ, we were able to run at 14 petaflops on Sequoia, which is 70% at peak on 1.5 million ranks, and 90% parallel efficiency, 3.6 trillion particle benchmark. So this shows you, yep, on the BGQ we can run a super large problem. And on a completely different machine like Titan, we can equivalently run 20 petaflops at 77% of the machine. There's a lot of different explanations for what these curves are. This is our most recent. But the point is that we're tackling this diversity because we need to. And it's a problem that, as the previous speakers have talked about, isn't going away. And in some way, you will be exposed to this if you remain in this field. So that's it. I would just like to acknowledge the CSGF. I appreciate all of your support. And of course, I'm super thankful for the money. And I hope you felt it was spent wisely. And I will take your questions if I still have some time.